Hi, my name is Tianedra Simmons. I attend North Carolina A&T. I'm a sophomore, and my major is nursing attendant.
My name is Frank Williams. I'm a sophomore. My current major is journalism and mass comm, and I attend North Carolina A&T.
I have chapter 9, nuclear radiation. So the most common naturally occurring isotopes are the alpha particle, the beta particle, and the gamma ray. The alpha particle is identical to the element helium. So basically, it has 2 protons, the mass of 4, and a charge of a positive 2. The beta particle is a high energy. Its charge is -1, and it has a mass of 0. And the gamma ray, which is pure energy, it has high energy, and it's only energy. So when you write it out, that's the 2 zeros is representative as it has no mass or no charge. Positron is a positive charge, and it has a mass of 0 as well. And the positron also represents the B, like the beta particle, but the only difference is with the beta it's a -1, and with the positron it's a plus. So radiation protection, proper shielding is necessary due to high volumes of exposure to radiation can be very harmful. The different type of particles, again, our alpha particle, which has the highest charge of radiation, and the protection that should be used is our lab coats. The beta particle moves faster than the alpha particle. The radioactive decay the nucleus is spontaneously breaks down by emitting radiation. The unstable nucleus undergoes alpha decay by emitting the alpha particle. So for the beta decay, as far as the equation is set up, it is the mass of radioactive nucleus plus the mass number of the new nucleus. They're the same atomic number. For the positron emission, the mass number of radioactive nucleus and a new nucleus are the same, and the atomic number is increased by 1. So the most common measurement for radiation is the Geiger counter. The unit is BQ. And some other ones are RAD, which is radiation absorbed dose. And this unit measures the amount of radiation absorbed by a gram of material, such as body tissue. The REM, which is radiation equivalent in humans, measures the biological effects of different kinds of radiation. And so as far as being exposed to radiation, we are exposed to radiation every day that naturally occurs from us. I know it's included in potassium 40. It's basically any food that includes potassium. For the beta particles, if it's exposed at high rates, it can just basically it'll burn the skin if the radiation is exposed to it. For the gamma ray, it's the most extremely hazardous particle, and high dosage or lethal dosage, it will kill you. And for that, it's like lab coats or plastic composites. So a few examples of radiation in lethal doses are the atomic bombs that were dropped on Hiroshima and Nagasaki. Those people, a lot of people did die immediately. And all the radiation in the body caused them probably different cancers and, all types of things of that nature. So as far as for interactive websites, here, which are listed below, are the interactive websites that you can click on and go to.
Okay, so for section 9.4, it covers the half-life of a radioisotope. And the half-life of a radioisotope is the amount of time that it takes for one half-life of a sample to decay. Also, a decay curve is a diagram that shows the decay of a radioactive isotope for each half-life. So, dating use of half-lives, carbon material in the bones of humans and animals, it assimilates carbon until their death. So meaning that it's present until, the person's demise or the animal's demise. So using carbon dating, the number of half-lives of carbon from a bone sample determines the age of the bone. Now, Section 9.5 covers medical application using radioactivity, and determining the condition of an organ in the body requires radiologists to use radioisotopes to concentrate in that organ. And cells in the body don't, there's no difference pretty much between cells in the body and, a non radioactive atom and a radioactive one. So radioactive atoms can be detected because they give off radiation. So that's the way that they're able to determine that. Also, scans with radioisotopes, an apparatus called the scanner is used to produce an image of the organ. So pretty much scanners, they're pretty, what it does is that they move across a person's body to detect, whether somebody has a disease, whether they have a blood clot, or just anything wrong with their internal system. So that's pretty much what that's used for. Um, Gamma rays from the radioisotope in the organ, they can be used to expose a photographic plate. And what the plate does is that it produces a scan of the organ. So that's how they're able to go in there and see if there's anything wrong with a person as well. So a scan producing an area of radiation, pretty much what it does is that it's able to find out if the person, if there's any kind of disease of the organs, as well as a tumor or even a blood clot, as I stated before. The next thing is a positron emission tomograph, and the positron emitters with short half-lives, such as carbon, nitrogen, oxygen, and fluoride, they're used on position emission tomographs. So a positron emitter isotope life is fluorine, and you can actually combine that with substances in the body like glucose, and it's used to study brain function, metabolism, and the flow of a person's blood. And the last section, which would be section 9.6, it pretty much pertains to fission, if I'm saying it right. And what it is that it begins when a neutron collides with the nucleus of a uranium atom. So in the 30s, scientists actually used uranium, I believe 235, with neutrons, and they discovered that uranium nucleus, it splits into two medium weight nucleated, which produces a great amount of energy. So that the uranium 235, pretty much what that does is that it's things that's used in like atomic bombs and trying to think what else. Um, I believe nuclear bombs, if I'm not mistaken. So pretty much like any weapon of mass destruction, like it's pretty much built using some type of uranium or the uranium 235. Also, pretty much heat from nuclear fission. That's pretty much was used to make electricity. So that's how we get our electricity. Also, nuclear power plants supply about 10% of the electricity of the entire United States. So, it's something that's very vital, but it can also be something that's extremely dangerous as well. Okay, and another interactive website that I found was pbslearningmedia.org. Now, this website is informative as well. The only pretty much complaint that I have about it, well, not a complaint, but the website is more, like kid friendly. So, pretty much if you're an adult, you'll probably be, just a little amazed at how, easily you can navigate through things. But it's still informative, nonetheless.